So I have bits and pieces to finish up from the section we're working on. I forgot to tell you the other day there is an important matrix that has the property that if you multiply any m by n matrix by the n by n matrix that I have in mind, you get A back. And if you take the same matrix with shape m by m and multiplied by A, you also get A if you do it in the other order. This reminds you of what in the real numbers?
Identity.
The multiplicative identity, 1. So the question is, I'm not going to keep writing the n by n, but this is called the n by n identity matrix. And it's not too hard to figure out that the matrix that does that is the matrix that has 1s on the diagonal and 0s everywhere else. So if you actually think about how you multiply matrices, for example, think about this one. If I took A, whatever he was, and I multiplied by the n by n identity matrix, what I'm really doing here is multiplying by the matrix whose columns are what?
Oh, the standard basis.
Standard basis vectors in Rn, right?
Yeah.
So what do I get when I do that? I get the answer that has A times E1 in its first column, A times E2 in its second column, up to A times En in its last column. But what is this?
1 times the first column of A, 1 times the second column of A.
Right, this is the first column of A. This is the second column of A. Up to the end. So you get A back. And you can similarly think about doing it with the m by m version in front and think about multiplying. And you'll get the same thing with rows, and you'll get the m rows of A back. Okay? So this identity matrix is going to come up a lot in what we do, including today. All right, so basically what I want to do for the rest of today is talk about 2 more things to do with matrices. The first is the transpose operation, which I mentioned the other day. And the second is something called inverses, inverse matrices. So these are the last topics that are in this section. So let's first talk about transpose. So I told you the other day that if you took a matrix A and you transposed it, it turns it on its side. And the symbol for this is a little t superscript there. So if you had an m by n matrix A whose ij entry so that's the ith row, jth column, ith row, jth column. Where does it end up? It ends up in the jth row and the ith column. So you've turned the ith row into the ith column of the transpose. Or, if you prefer, you've turned the jth column into the jth row. So the the ji entry of a transpose is the ij entry of A. So we've already noticed that if I took a vector x and a vector y, both in Rn, that you could think about dot product dimension. Same time. If you took x and dotted it with y, you would do x1, y1 plus x2, y2 plus x3, y3, etc. And the point is that more or less, so I'm going to put quotation marks because I'm sure somebody's going to have a complaint, that if I took x and turned it on its side, so I'm going to write that this way. Think of a vector here, can be thought of as a n by 1 matrix. Right? Good. A vector in Rn, so it's got n entries, 1 going this way. So when you transpose it, it becomes a what by what? Okay. So I'll turn it on its side, and then I'll multiply it by y. Now, according to the rules we have for how you multiply matrices, what do you get when you do that?
A 1 by 1 matrix with the dot product as the only
Right. So Dan, are you now going to agree why I put the quote marks?
Yes.
Does everybody see the issue? This is really a 1 by 1 matrix.
That's actually
This is really
a number.
a number. So we're going to make a convention when we write this that we're thinking of a 1 by 1 matrix as a real number, just it has bars around it officially. Okay? So we're identifying the 1 by 1 matrix with a number in it with the scalar, and we aren't going to worry about the distinction. Okay? So probably I should appoint Dan to be in charge of worrying about this, and if we make a mistake where it doesn't make sense, he should alert us. Okay. So, with that interpretation, I now want to get a very useful formula, but I need one thing before that. Suppose A is m by n, and B is n by p. Then I can multiply A times B, and it will be what? What is the transpose of the product? It's going to be P by M. You think there might be a formula?
Yeah.
So let's do a simple case. Let's do a 2 by 3 by a
3 by 2.
or what?
Well, 3 by 4.
3. Oh, I don't want to do that much. Let's just do a 3 by 1.
Okay.
So I would get a 2 by 1. And it would look like this, I hope. If I transposed this,
Yes,
14.
it would be a row with 14 and 26. How could I get that row from these two matrices
probably
directly?
transpose them and inverse them.
So
Transpose times transpose.
transpose and
Switch the order.
switch the order. So fact, the transpose of AB is the product of the transposes in reverse order. I'm going to have an affectionate name for this in a few minutes in a different setting. Why is it in the reverse order?
So the dimensions match up.
Yeah, I mean, if the dimensions are going to match up, that you have to switch the order, because A transpose is n by m, B transpose is p by n, and the only way to get the middle guys to match is to reverse the order. Now, we can actually just see it. If you thought about transposing here, when you're computing this product, you're obviously doing the same dot product that you're doing here, which gives you the 14. And when you're doing this product, this guy with this, you're obviously doing the same dot product that you're doing here, doing the second row with that column. So this is a total general fact, and I think the book writes out an official proof with notation. But okay. This is very useful. So here is the first application of that. So this is what I referred to the other day as Ted's favorite formula, which Justin has never forgotten. Okay, so suppose A is n by n, and I want to write AX for some vector x. So x has to live where? Has to be an Rn. So this is a vector that lives where? How many components does this vector have?
N.
Again?
N.
M.
M.
M. So AX is an Rm. So if I want to dot it with a vector y, where does y have to live?
N by L, or something by.
No, it's just a vector.
M. is what-
M. So this is the setup. So I'm just to help you here, I'm going to color code the M and the N. This dot product is living in a dot product of vectors in Rm. And I want to rewrite it as a dot product of vectors in Rn. So I'm putting a green dot for Rn here. The question is, what vectors am I dotting in Rn?
A transpose Y. X dot A transpose Y.
X dot A transpose Y. Basically, that's the only thing you can do to get vectors in Rn. You have to have X. And what can you do to Y that'll put him from M to N? Well, you have to do A transpose. That'll flip him back to Rn. Just count.
I missed why y has to be in Rm.
Because I said this vector was in Rm and I wanted to dot it with y, so it has to live in the same space.
So A is n by n, and when you dot it with n,
And
Wait, so you multiply a by a vector x, you get a vector that lives in Rm.
you have n by n and n by 1, and then you end up with the n by 1.
So a
right, okay. That I
times
follow.
x is a vector with the same number of rows as a has.
Okay, so it's n by 1, which you just consider m.
Yes.
So I should put the color coding continuing here. Right, so this is officially m by 1. This is m by 1, I dot the two
Okay.
vectors. All right, so let's try it out with my example here. So here's a, here's x, and let's just pick a random vector y for me that lives in R2.
1,
Vector in R2, please.
1, 0.
2.
Oh, come on. 1, 2, all right. So let's do the example here. So with this a and this x, what was it, negative 105? And you guys gave me, after much premeditation, 1, 2. So let's do ax dot y. I already computed ax. I hope it was right. Dot it with y. All right, this is the hard part. What's the answer? 66? Goes back to the, oh, never mind. Now let's do x dotted with A transpose y. So what's A transpose y? Well, we have to do that. A transpose is this. Well, let's see. So x is this. And A transpose is 1, 2, 3, 4, 5, 6, and I have to multiply that by 1, 2. So I have to do negative 1, 0, 5 and dot it with what vector? So what's this matrix times 1, 2? It has 3 entries. What are they? 9, slow down. 9,
12,
12.
15.
You guys are fast, okay? Now comes the hard part. What's 5 times 15?
7
Minus 9.
is
Yay! All right. So is this a big mystery or is it obvious to you all why it works?
it's in the middle.
It's in the middle.
Some gray area.
Click in that middle space.
Isn't magic.
No, it's not that magical. Proof. Proof's so easy it fits right there.
Oh, wow, okay.
What did we say we could think of a dot product of two vectors as doing? Multiplying the transpose of the first by the second. So ax dot y equals with Dan's quote marks
Yeah.
ax transpose times y. Now, how do I take the transpose of a product? We use that fact. So what do I write down?
No, X transpose, and then A transpose Y. So then you can undo the transpose.
Now, I'm going to be officious here. What do we do officially when we're being officious?
Use Commutative.
No.
Associative.
Reassociate, right? Regroup. So that's being pedantic, but it's important to understand we're using it. And now what's that?
You can use that back.
That's just x dot.
You go backwards.
Right.
Did you like calculate out that space right there? Because that just worked out perfect.
You'll never know. We'll never know.
Transpose on that.
Wait, how'd you get rid of the transpose on X?
Because I used this fact,
The undotted. Yeah, it's
where'd it go?
it's down
Up there. So x transpose times a vector is the same as dotting the two vectors. That's the same fact we used here.
Yeah.
When we, right, we did, the dot product is the transpose of the first vector times the second. Now I unused it. I used it again, but backwards. You see it, Philip?
Yeah.
Okay. All right. So to convince you that this is actually more interesting than it looks, I have my other bone that I throw to the economists. Of course, at least one of them is missing. So I want to use that formula to give you what I think is sort of a cool economics interpretation. So I'm going to call it real world. I don't know if those are Dan's quote marks or my own this time.
Those were your quote marks. I just explained why you put them there.
Are you're not taking ownership?
No.
All right. So I want to give you an application. So remember the other day we talked about how you could have commodities, each of which had a certain price per unit, and you could take the price vector and the commodity vector and dot them and get the total expense of buying all those things. So let's suppose, again, it's just before lunch, so I guess I won't make you too hungry. So let's suppose you're going to produce a bunch of different kinds of cookies and you're going to sell them to your friends. And what you want to figure out is how much to charge your friends for each dozen cookies.
More than the cost.
Okay, you get to put, you can add profit, being greedy the way I know you are, you can add profit after we do the computation.
As a scale on top, right?
So suppose I have P, which is a price vector for my various ingredients. So to make these cookies or to build a building, you're going to need a certain amount of lumber, and you're going to need a certain amount of concrete and a certain amount of labor, or you can put all the things in, it doesn't have to be food. But you're going to have various ingredients that are needed to make various kinds of cookies. Each of those ingredients will cost a certain amount per unit. Okay? Now, what is the missing ingredient from this story? If I'm going to take ingredients,
The actual
well, I've got prices.
physical amount that you need.
No, but there's, if I'm going to want to produce different kinds of cookies. Say I want to make chocolate chip cookies and oatmeal cookies and ginger cookies and I need something that tells me what?
The recipe.
A recipe.
Right.
I mean, I don't care about how long I have to stir the butter and when the eggs go in and when the sugar goes in, but I do need to know to produce a dozen of these cookies, I need so much flour, so much oatmeal, so much butter, so much sugar, so many walnuts, and so forth. So I need a matrix that encodes all my recipes. So what do I need to feed into the recipe matrix, and what will it tell me comes out? No, P's not there yet. So I'll give you a hint. I'm going to make A be n by n, we have two things going on here is
You feed it.
what the ingredients are
Right, and then
and what different cookies we're producing
Right.
and how much.
many of each type of cookie you want, right?
So what should be m and what should be n?
M is the ingredients, N is the absolute.
Shouldn't one of them, if you want to,
Other way
like, all
around.
whole price, shouldn't one of them be 1?
So do I not want y here to be the output, which is the number of dozens of each kind of cookie?
Oh, that's what
Well, no, that
No,
wouldn't
you
work,
want X.
because I want to have a vector that's going to compute the cost of my ingredients. So y had better be my ingredient vector, and x had better be,
The,
No, sorry.
the like number of each cookies you want, right?
the number of dozens of each cookie. So it's going to be the quantity
Right.
of cookie vector. Does that now make sense? What's going to go across the rows of A? Suppose I want to do 6 dozen oatmeal cookies and 2 dozen sugar cookies
With no chocolate chip
Oh, your
cookies,
columns.
right?
and 7 chocolate chip dozen.
Column should be the rest.
So what should go?
Three.
Actually, really, my matrix should have many more rows.
Yeah, once you make it really bland.
You're making bland.
What do? Well, this tells me how much butter I need to make a dozen of each kind of cookie. Right? Butter per dozen of oatmeal, I need, say, ½ pound, and to make a dozen of sugar cookies, I need 3/4 pound, and to make a dozen chocolate chip cookies, I need a ½ pound of butter. This would then compute for me how many pounds of butter I need. And you would go on and you put flour, and you put eggs, and you put chocolate chips, etc.
It's a lot of butter.
So what my recipe is going in the columns here, right? For each kind of cookie, the ingredients I need are going in that column. Agreed? Well, how much does it cost me to produce these cookies?
P times
P times
Y.
Y.
P dot y. I have to have my price vector for all these ingredients I'm buying. So that's P dot AX. And what does Ted's favorite formula tell us?
K transpose. K transpose P dot X.
It tells you it's the same as the dot product of A transpose P with X. This is my X here. So what is the meaning of this side, and what's the meaning of this side?
You take the prices of all your ingredients.
So this is the total cost that you incur to bake the cookies, not counting your labor. Right? This is the total expense of the ingredients. But this side has dotting with an X, which is the vector that tells you how many of each dozen cookies you're producing.
So it's the price per cookie.
Price per dozen.
Price per
The
dozen.
number of cookies.
This is going to be how much price you should charge for each kind of cookie per dozen to break even. So this is the price to charge per dozen cookies vector.
Is this your way of introducing a cookie stand into that?
Isn't that sort of cool? I mean, this matrix equation is doing the computation. Of course, it's obvious when you think about it, but it's computing what it costs you to make a dozen of each kind of cookie, and that's what you better charge if you want to break even. Okay, so if you think that formula is useless, then you'll have to just figure this out the long way when you try to sell your cookies.
So is this how like Insomnia does it? You know, how they charge their prices? Insomnia cookies.
Insomnia cookies.
And then you got
Oh,
delivery
no,
charges.
but they add like 100
Yeah,
out.
they only.
Yeah.
Right, I mean, so, by the way, you certainly could include labor as an ingredient.
Yeah.
So if it was a lot harder to make one kind of cookies, if it took you an hour versus 10 seconds, you would put in some labor costs as well. And then there's some profit that I'm sure they add.
It's a 10 cent. Killing it. No.
All right, so a couple minutes on the last thing and then we'll finish it up tomorrow. So the other thing I want to talk about briefly is the notion of an inverse matrix. And we'll, as I say, I'll do a bit more with it tomorrow. So Matthias had a revelation the other day when we were talking about what matrix multiplication means. Matrix multiplication means composition of functions. What you might want to ask yourself, is there a matrix that I can multiply that undoes what multiplying by A does?
A inverse.
That would say, is there a function, A does something as a function, is there a function that undoes it? That's what inverse functions are, isn't it?
Right, yeah.
I tell you a number, you square it,
You take-
somebody unsquares it and gets you back the original number, provided
It's possible.
it was positive. All right, so you have to worry about domain and range. So, definition, let A be an n by n matrix. Notice it is starting out what?
N by N.
Square.
Square. We say B is, we say A is invertible if there is an n by n matrix B satisfying A times B is the identity, n by n, and the other order too. So if you remember your years ago pre-calculus, or whatever it was called in high school, when you did inverse functions, you had to be able to compose in both orders to get back to your original x. So that's, B is called, if so, if there is such a B, B is called the inverse of A, and is you write A to the negative 1. It does not mean 1 over, please. There is no such thing as 1 over a matrix or 1 over a vector. Does this A have an inverse?
Yes.
Yeah, because it's a square.
No.
No.
Zero. So.
We don't know that word.
Okay.
What happens if you multiply by any B? What's going to happen?
Zero.
Where?
The second.
It's a zero matrix. It equals-
No, 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 no.
You're gonna have the second column.
You just-
Oh, wait, no, never mind.
But what happens when I get down to the second row?
Zero, zero.
You're going to get zeros there. So you can't possibly get the identity.
Because you want to.
No matter what B you put, you're going to end up with zeros there. So you cannot get the identity. There can be no inverse. So A is not invertible. Okay? What about this matrix?
Yes.
Well, now you do a bunch of trial and error. And just for some bizarre reason, I make up the following matrix. I say to myself, let's try it. Threw you off that time. What do I get?
1, 0, 0, 1.
1, 0. Notice these are orthogonal. And notice these are orthogonal. So I get a 0 there. And what's the last one? 1. Well, maybe that's the inverse, maybe it's not.
You still have to check the other multiplication.
I have to check the other multiplication. Three minus 2. These now are orthogonal. Isn't that cute? Oh look, so are these.
Crazy how that works.
Minus 2 plus 3. Yes. So this guy is the inverse.
For some bizarre reason.
So what we will discover tomorrow is that there is a general formula for 2x2 matrices. You will learn later this semester how to do general inverses by a procedure, and then next semester you'll learn yet another way to do it by a different procedure. And I want to then also show you tomorrow some applications of this to stuff we were talking about back in sections 1 and 2. Okay.